All right. Good morning, everybody. So welcome to the last lecture class for Math 175. Hindi, pwede pa pala tayo mag-meet to talk about the project on Wednesday. Pero this would be the last full-on lecture that we will have. Tapusin lang natin yung module number 12, ano? And remember here, we're talking about multi-step methods. So may isa na lang akong class ng methods na i-discuss sa inyo. But before going there, just a couple of announcements. I already uploaded an updated module 12. So in the last 2 pages of the module, you will see the last exercise for the course. This is exercise 6, and it's going to be about the Rangekata and the Adams-Bashforth methods. So here in this lab excerpt, we'll just be going back to the epidemic model that we considered last semester, pero nirecalibrate ko siya ng konti because hindi ganun kaganda yung graphs na nakuha natin because apparently the transmission constant I pick is still very large. So ito medyo binabaan ko na siya. So yung transmission constant is this. Okay, ito na yung gagamitin natin na transmission constant. And yeah, so edit nyo lang ng konti yung nandun sa codes nyo. The reason kung bakit na overestimate ko yung C nga pala ay siya yung constant that is to be multiplied to the product of the number of healthy individuals and the number of infected individuals to get the transmission rate. So ang unit of measure para kay C ay per person squared. So kaya dapat medyo mas maliit pa siya dun sa sinet ko last time. And I think I kept the same. Oh, pinababa ko ba yung mortality constant? Pinataas ko yata yung mortality constant. It's now at 1%. I think last time it's 0.01%. So I made these adjustments. Mag-pretend na lang tayo na medyo may bagong information na dumating sa atin mula dun sa ibang lugar. So here, para less morbid yung usapan. So sabi ko, we'll be playing the role of a policymaker. Now we want to propose or to look at the effect of the epidemic in Laguna. All right, so titingnan natin hypothetically ano yung mangyayari kung makakapasok sa Laguna yung disease. Now nakuha itong data na to mula sa kunwari sa isang katabing town kung saan meron ng epidemic, and then we want to see the effect of not introducing mitigating or intervening actions or measures sa pag-spread ng epidemic. Halimbawa, papabayaan lang natin. So mag-work ba yung pagkakaroon ng natural immunity? So assuming na wala tayong interventions, ito yung model na magaganap. And this model is quite limited because again, we are just considering 3 compartments. So healthy, infected, and dead or dead. So tapos ang assumption natin kapag ikaw ay infected, there's only one way to get out of the infected class. Yun ay kung you will succumb to the death, succumb to the disease rather. So kaya medyo limitado yung ating model. Kung gusto mo ng mas realistic na model, then i-assume mo na makakalis ka dun sa infected class in 3 possible scenarios. Number 1, you die. Number 2, you recover, but you go back to the healthy individuals na susceptible to the disease, or you become immune to this disease. So pwede kang magdagdag pa ng mas maraming compartment, but that will require us to have a more complicated model. So ito, simple lang. Tapos ang gusto kong tingnan ay kung ano yung mangyayari kapag walang intervention sa ginanap. Halimbawa, ilang days before mag-peak yung number of infected individuals. Alright? Tapos gaano karami yung infected at that time. Tapos kailan magiging equal yung number of healthy at number of infected individuals. So that is my intuitive guess for where the transmission is at its optimal level. So kaya tingnan natin kailan nag-equal yung healthy individuals saka yung number of infected individuals. And in some epidemiological models, ito yung crucial timeline kung kailan magkakaroon ng peak yung transmission, so kailangan mag-introduce tayo ng intervening actions. Tapos, we want to see also, when will the number of deaths equal to the number of infected individuals? Ito naman yung time kung saan medyo bumababa na yung transmission ng disease due to an unfortunate reason na umuunti na yung infected individuals kasi most of them were already dead due to the disease. Tapos a grim scenario is, halimbawa ikaw yung policy maker, kailangan mong takutin yung mga, or ikaw yung modeler, so kailangan mong takutin yung mga policy makers. So, no, gusto mong sabihin sa kanila, in this number of days, 90% na ng population ay mamamatay na. So that would be our deadliest deadline. Actually, medyo late na nga ito to give intervening actions. So, no? So kindly go through and read the little bit long description of the problem or the exercise and make sure you answer all of the questions. Kasi I graded yesterday yung lab exer 5 ng D2L. May ilan na mga nakalimot na sagutan yung ilang tanong dun sa lecture dun sa lab exers. So I had no choice but to give deductions for them. So make sure you answer all of the questions specified in the laboratory exercise. Oh, by the way, if you already submitted your lab exer 5, check your inboxes because I emailed yesterday ano yung password para dun sa PDF ng answer key ko sa lab exer 5. Okay? So, and then hopefully I will be able to release an answer key to the last lab exer on Monday. All right? Tapos i-grade ko na rin siya para problem set number 3 na lang at saka project yung kailangan yung pag-isipan. Now, for the problem set, I'll give you the problem set on Tuesday, 8 a.m. para tapos na yung lab exer. So pwede na kayo mag-focus sa problem set and the deadline for the problem set would be at June 9 initially. So just let me know if you need more time. Titingnan ko kung kaya ko pa siyang i-adjust to a later date. Okay? And what else? So final project, I hope you guys already answered the Google form. So nakalimutan kong i-summarize, pero after our call, I'll start grouping those who answer the Google form na wala pang makaka-group dun sa project. And then on Wednesday, pag-usapan natin ano yung mga posibleng topics para sa project, okay? So but for now, let's finish up module number 12, ano? So sa module number 12, isa na lang yung topic and this would be the Adams Moulton Methods, okay? And this would be quick because the Adams Moulton Methods are very similar to the Adams-Bashforth methods, okay? Ang pinagkaiba lang nila, posible maging implicit yung Adams Moulton Methods, ano? So, and I think this is a fitting way to end our Math 175 journey kasi nagsimula tayo sa 174, di pala 175 journey. It's a fitting and poetic end to our numerical analysis journey because remember in 174 we started a course by talking about Lagrange interpolating polynomial, and now we have come full circle and we're talking about Lagrange interpolating polynomials again, albeit in a more advanced setting, ano? So paggamit ng Lagrange interpolating polynomial sa pagsosolve ng mga ordinary differential equations. Kaya naisip ko nung sinusulat ko to kagabi, sige na nga, last topic na tong Adams Moulton kasi ang ganda. Dito tayo mag-e-end pa rin kay Lagrange, okay? Now, as I was saying earlier, the only difference between the Adams Moulton and the Adams-Bashforth methods is that Adams Moulton methods might be an implicit method, okay? If you remember, multi-step methods are characterized by equation 12.1. So ganito yung target natin para sa mga M-step methods for solving ODEs. Ano? Now, if you will see that in the Adams-Bashforth methods, B sub 0 is equal to 0, so that the right-hand side of our ansatz or our template for the methods, I devoid of a term involving W sub I plus 1. So that makes it implicit because if there is no W sub I plus 1 on the right-hand side, then we can easily solve for W sub I plus 1. So we will have W sub I plus 1 equals a function phi, which only depends on H, F, ano pa ba? T sub I hanggang T sub I minus what? Minus M plus 1. Again, t sub I, comma, w sub I minus m plus 1, comma, dot, 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 hanggang kay w sub I. So yung right-hand side ng method ay kaya nating isulat purely in terms of w sub i's and previous values ng previous values sa time steps. Ano? So nag-0 si b sub 0. Pero itong Adams Moulton, pinapayagan na non-zero si b sub 0. And that's why it could be a little problematic because if f is complicated, for instance, if it's a transcendental function, then we cannot separate or we cannot get rid of w sub I plus 1 from the right-hand side. So posibleng kakailanganin yung mag-solve ng isang nonlinear equation sa bawat time step para lang ma-solve si w sub I plus 1. Okay? So titingnan natin ngayon, bakit nagkakaganon sa Adams Moulton? Ano ba yung pinagkaiba nung derivation ng Adams Moulton mula sa Adams Bashforth? Okay? And the idea here, and then the answer there is kasi pinapayagan natin na pinapataas natin yung degree ng interpolating polynomial natin by sa function f by allowing t sub I plus 1 to be one of the interpolatory abscissas. Okay? And then the process ng derivation ng Adams Moulton methods ay kaparehas na kaparehas nung Adams Bashforth except for that first step. And this is what I'm saying. So, di ba si f, pinapalitan natin siya ng interpolatory polynomial, right? Sa Adams Bashforth, simula siya kay t sub I plus 1 minus m, papunta kay t sub I. So we are using m points to interpolate f. So that gives us a degree at most m minus 1 as interpolant for the function f. Pero sa mga Adams Moulton methods, sinasama natin si t sub I plus 1 as one of the interpolatory abscissas. Okay? So that means we have a total of m plus 1 points to be used in the interpolation. So we will get an interpolating polynomial of degree at most m. Okay? So tapos itong interpolating polynomial to, given pa rin ng Lagrange form you see as p sub m on the screen. Tapos, ang kagandahan nga lang nito, na nagdagdag ka ng isang t sub I or isang time value dun sa interpolation process na dadagdagan ng isang degree yung error term. So, ibig sabihin, mas bumababa ng isang degree yung error involved due to the truncation of the interpolatory polynomial. All right? So, remember last time, sa Adams Bashforth, yung error dun sa Lagrange interpolating polynomial ay mth derivative ni f evaluated at some number c and x of c all over m plus 1 factorial, and then what comes with it is a degree m polynomial. Dito sa Adams Moultons, nadagdagan siya ng isang degree. Nadagdagan ng isang order yung derivative, pero ang crucial thing doon, nadagdagan ng isang multiplier, isang linear factor yung nandito sa product. So that means we are gaining 1 degree of accuracy. And that's the advantage of including another time step. Okay. And then from here on, we will just follow what we did for Adams Bashforth. Ano? Sa Adams Bashforth, ang ginawa lang natin, in-integrate ko both sides to get the b sub i's dun sa equation 12.1. Now, if we do so, okay, actually, hindi ko na pala pinakita yung mahabang derivation o yung generic formula. So, mangyayari lang doon ay pag in-integrate natin si P, okay, from T sub I to T sub I plus 1, okay, actually, dito siya mapapasok, no? Pero linearity of the integral tells us that we can put the integral here, dt, tapos times this constant, which is a function value, right? So, ibig sabihin, yung mga b sub i's nakadepende lamang doon sa integral ng Lagrange basis polynomial L sub j. Pero nakita na natin to doon sa derivation ng Adams Bashforth methods. Okay? Now, pakita ko lang yung specific derivation para sa two-step Adams Moulton methods. Tatawagin natin siyang AM2. Okay? So, ibig sabihin, kung two-step siya, si F ay i-interpolate ko using 3 points. T sub I plus 1, T sub I, and T sub I minus 1. So ibig sabihin, bawat Lagrange basis polynomial ay magiging degree 2. Kasi kung 3 interpolatory abscissas, so magkakaroon tayo ng interpolating polynomial of degree at most 2. Alright? So yung basis, yung little l sub j's, yung mga Lagrange basis polynomials ay degree 2. At ito sila respectively. Alright? Tapos ito naman yung error term. So makita nyo, ito ay isang cubic polynomial. Alright? And that is to be expected. Now to get the formulation for AM2, all right, yung Adams Moulton of 2 steps, ano? So kailangan ko lang i-integrate itong mga Lagrange interpolating polynomial para makuha yung mga b sub i's doon sa equation 12.1. Okay? Now I will integrate them over the interval t sub I until t sub I plus 1, but in order to get a nice integral there, gagamitin ko tong substitution na to. Pero actually, hindi naman siya kailangan. Pwede nyo itong ipakompute kay Mathematica, ano? Or kahit kay MATLAB, polynomial lang naman to. So, madali niya yung masasolve. Alright? So, it turns out that b sub 0 will be 5h all over 12. b sub 1 will be 2h over 3. And b sub 3 would be negative h over 12. Okay? Tapos, yung local truncation error ay ibibigay naman nung integral nung error term. So ito yung i-integrate natin from t sub I until t sub I plus 1. Now, if you do that, you will get this. Okay. Now, we'll see here that this two-step method has actually is, hindi pala to given. Dapat ito ay is dependent on. Okay. So nakadepende siya dun sa integral ng error term. Kasi well, divided by h. Yeah, kasi di-divide ko pa siya by h later. Ano? So if you integrate Rm, you get this quotient, all right? And c hat here is a number between t sub I and t sub I plus 1. So with all of these things known, pwede kong makuha yung equation 12.1 as this one, all right? Kasi di ba pag in-integrate ko yung, remember yung magkakaroon dx over dt equals integral ng f from, actually hindi pa pala integral. So integral from t sub I to t sub I plus 1 ng dx ay equals sa integral ng t sub I plus 1 ng f dt. Alright? So ito yung integral na nakuha natin mula dun sa pag-i-integrate ng Lagrange interpolating polynomial. Tapos ito ay magiging x sub I plus 1 minus x sub I. Para makita ko really what is the local truncation error, I need to divide both sides by h. Alright? I-divide ko by h yung integral na nakuha natin. And I will come up with this integral. Okay? Kaya gusto ko siyang isulat ng ganito na yung right-hand side ay isang, what you call this? Ay isang difference quotient para makita ko ano talaga yung local truncation error, alright? Because the local truncation error is the error incurred by replacing the derivative by a difference equation, you know? So yung dx over dt napalitan siya ng x sub I plus 1 minus x sub I all over h equals this guy. And the error term here actually is this. Okay. And you see that this two-step method is of order big O of h cubed as promised. Kasi na-note na natin kanina, kasi mas malaki ng isang degree yung error term dun sa Lagrange interpolating polynomial. So ibig sabihin si Adams Moulton magkakaroon ng isang degree na mas mataas kesa dun sa Adams Bashforth. Okay? So that means, yeah, this is to be expected that the local truncation error for AM2 is a big O of h to the third compared dun sa AB2. So yung Adams Bashforth na 2 steps din, pero of order big O of h squared lamang siya. Right? Now, after going through this hindi pa naman siya convoluted, hindi pa siya ganun kakomplikado. But at this point, I can just ignore the error term. And then from this guy, compute for replace all x sub i's by w sub I plus, by w sub i's, and then solve for w sub I plus 1. And we will get this formulation para sa AM2, right? Now again, this is a two-step method, but all we know from the given IVP is the initial condition. So kulang tayo ng isa pang initial data. Kasi kailangan at every time step, dalawa yung ginagamit natin. So we cannot compute W sub 1 using AM2 kasi kailangan ko doon ng dalawang initial data. Isa pa lamang yung meron ako. Just to fill in the gap in our data, so pwede ka mag-employ ng isang one-step method para ma-compute si W1. Pero take note that AB2 or sorry, AM2 ay isang order big O of H cubed na method. So dapat ang pipiliin mong pang-compute kay W sub 1 ay isang order din na big O of H cubed yung accuracy. Okay? So hindi ka pwedeng basta mag-RK2 rito katulad nung ginawa natin sa AB2, alright? Kasi mas mataas ng isang degree itong AB2. So kailangan mo mag-AK3 o kaya mag-Taylor's T3 so para makuha si beta. But once you have alpha and beta, you can proceed with the iteration given in equation 12.10. You can compute W sub 2 using W sub 0 and W sub 1, and then W sub 3 using W sub 2 and W sub 1, and so on. But you see the kicker here. Ano yung price that we had to pay to get 1 degree of accuracy? The right-hand side of equation 12.10 now might involve W sub I plus 1. So magiging problematic ito kapag hindi natin kayang ilagay yung W sub I plus 1 dun sa kabilang equation. Okay? But we'll talk about that later kasi ganun yung ipapagawa ko sa inyo sa problem set number 3 sa computational part. So sabi ko nga last time, halukayin nyo na yung mga root finding techniques na root finding programs na sinulat nyo for unit number 1. Okay? And then ang ganda rin niya, poetic din siya because we have come really full circle kasi ginawa natin yung unit 1, babalikan natin para tapusin yung unit 3. Now, if you are patient enough, you can try to derive the 3-step Adams Moulton method at i-verify nyo na ito yung makukuha yung formulation. Now, in this formulation, we see that still, or that as expected, the order of the error is big O of H to the 4th. So, kailangan para makuha yung dalawang kulang na initial data, kailangan ka mag-RK4 o kaya mag-T4 or any method of order 4. Tapos, ito yung formula para kay W sub I plus 1. And the local truncation error is a factor of negative 19 over 720 times yung H to the 4th times some constant. Tapos nakikita nyo, ang ganda na ng order 4 kasi ito palang coefficient, panalo ka na dito Kasi negative 19 over 720, that's very small, alright? So parang nabawasan pa ng isang logarithmic order yung error kasi I think this is less than 0.1, So yeah, napakalaki yan yung nag-gain natin. However, this comes at a very heavy price. Now, kapag ka-complicated si F, lalo na kung siya ay transcendental, kailangan mo gumamit ng root finding technique. And what's the con to that? Ang problema sa mga root finding techniques, kailangan nating tingnan magko-converge pa ba yung root finding techniques na yon to the desired solution. Alright? Kasi hindi lahat ng root finding techniques ay nagko-converge, right? So, okay, pwede ka mag-bisection method, lagi yung nagko-converge, pero ang problema sa ang root. Tapos kailangan meron kang initial bracket. So ang dami mong consideration pag kailangan mong isolve etong implicit equation na to using a root finding techniques. Yung mga sureball na mga techniques na nagko-converge, bisection method and the regular false method, they will require an initial bracket. So ibig sabihin at every time step, kailangan kang mag-regular falsy or bisection method na kailangan pang isipin nag-hold ba yung premises ng root finding techniques na yon. Now, if you don't want to bother checking whether you have a nice bracket, meaning nagpapalit ba yung sign ni f of or ni W sub I plus 1 at saka ni W sub I minus 1 o kung saang interval ka man naroroon. So pwede kang gumamit ng iterative schemes. Pwede kang mag-fixed point iteration, pwede kang mag-Newton-Raphson, alright? But we have learned that those methods may not converge. Pwede ka rin mag-secant method, pero kailangan mong i-check kung nagko-converge pa ba sila depending on the initial condition. Kaya medyo matrabaho yung paggamit ng Adams Moulton. Okay? Lalo na kung implicit siya talaga, hindi mo siya kayang i-reduce to an explicit scheme. Now, this disadvantage ng Adams Moulton actually is addressed by introducing some predictor corrector methods. Na hindi ko na siya sinama sa module 12, probably you can explore it in your projects. Mag-discuss at mag-run ng ilang examples para sa isang predictor corrector method. Na instead na kino-consider mo ito or instead na sinasama mo explicitly yung W sub I plus 1 dun sa formulation o dun sa right-hand side ng formulation, pwede na lang mag-correct ka. Kung mag-run ka ng isang method na explicit, tapos mag-add ka na lang ng corrector term. So yun yung predictor corrector. So gagamit ka ng explicit method to predict what W sub I plus 1 is, pero i-correct mo ng konti yung prediction na yun. So yun yung tinatawag natin na predictor corrector methods. So maybe I can say a little something about that later, or to give you an example of a predictor corrector method. Pero tingnan natin yung example dito. Okay. Now, sa example 12.2, tingnan natin kung paano natin i-formulate yung two-step Adams Moulton method para dun sa IVP na kino-consider natin ever since we started the unit. So, yung IVP ng right-hand side ay 1 plus x over t. Now, kung isa-set up mo yung Adams Moulton, kailangan mo lang iset si W sub 0 to be equal to the initial condition 1 na given sa IVP. And then beta, which is your value for W sub 1, should be determined using an order big O of h cubed na method. Kasi nga si Adams Moulton na two-step ay big O of h cubed yung accuracy. So kailangan mong gumamit ng T3 o kaya ng RK3 para makuha si beta. Tapos pag nakuha mo na yon, kaya na nating isolve si W2, W3, and so on. Pero paano natin siya isosolve? Now, I will use equation 12.10. 12.10 nga ba yun? Yes, ito, 12.10. Pa-plug in ko lang si F to be 1 plus W over T. Okay? Kasi ito yung magiging itsura ng equation. So, ito yung formulation niya. Para kay W sub I, ito pala yon. Tapos lahat ng function f, papalitan ko na ng 1 plus W over t. So I will have, actually dito ko lang pala siya pinalitan kasi wala naman akong problema rito, right? Because they don't involve W sub I plus 1. So the whole point of this exercise that I'm doing is to hope that I can write AM2 as an explicit method. Otherwise, kailangan ko mag-root finding technique. Alright? Kaya ang in-expand ko na lang dito ay yung f of t sub I plus 1, W sub I plus 1. Bago ako mag-run ng root finding. Kasi dito pa lang, pwede ka na mag-apply ng root finding technique. Okay. Kaya lang, I am hoping na i-avoid yung paggamit ng numerical root finding. Baka naman kaya kong hanapin yung root using symbolic calculations first. So that's why I expanded F following the definition given in the IVP. And then, W sub I, mukhang kaya ko siyang i-separate. So what I just did is to distribute the multiplier and then transpose the term involving W sub I plus 1 to the left side. So I get this, okay? And then I can factor W sub I plus 1 from this guy. Tapos yung natitirang factor ay wala ng W sub I plus 1. So all I need to do is to divide both sides by this factor. And now I have reduced AM2 into an explicit method. Okay? So hindi pala siya ganon ka-problematic. Kasi kaya ko pa siyang isulat as an explicit method. But here we got lucky because little f is not that complicated. So, pero kapag siya ay komplikado, halimbawa, ang meron kang equation ay, halimbawa, meron kang W sub I plus 1, ito yung nangyari, H plus, ano nga yung multiplier niya? 5H over, W sub I plus 1 equals W sub I Plus halimbawa, meron kang 5h over 12 times sine ng t plus w sub I plus 1 times e to the ti minus w sub I plus 1 plus a bunch of function values. Ano? So ito yung problema. Hindi natin kakayaning i-isolate si w sub I plus 1 sa isang side ng equation. So if that happens, then we don't have any choice but to run a root finding technique to solve for w sub I plus 1 in that equation. Okay? So I think I will end here. So hindi ko na to simulate. Nilagay ko na lang siya sa an exercise. Try nyo na lang na i-simulate siya para makita nyo rin kung tama itong derivation ko. Hopefully tama yung algebra ko dito. Minano-mano ko to kaninang madaling araw, so baka may mga typos. So just let me know if you found some. Okay. Then try to implement it using these two guys. Okay. Now, all right. So I think that's it. The other topic that I was thinking to include in the course ay yung yung predictor-corrector methods. Pero nakakita na tayo ng isang ganong method from last time. Pwede nating i-treat yung RK2, specifically the Hoyne method or the Yoon method, na isang predictor-corrector. So, balikan nga natin yung Yoon. Nasaan na yung Yoon? Yes. So the Yoon method is an example of a predictor-corrector method. So ang predictor stage ay yung first stage, yung Euler's method. So employ mo lang to, that's fine. And then kailangan mo siyang i-correct. So meron kang implementation uli ng Euler, okay? Pero ito yung corrector term. So parang nag-a-adjust tayo dun sa ating initial prediction. So para makakuha tayo ng isang additional order of accuracy without using an implicit method. Because remember, Euler's is a big of H method. So para mapataas siya na ayaw mo namang gumamit ng implicit method, so kino-correct na lang natin yung nakukuha natin kay Euler. So we are correcting it by using this formula. So ito yung correction, ito yung prediction stage. Marami pa mga predictor-corrector methods. Ano? Some of them are aligned with the Runge-Kutta methods. So katulad nitong hindi ko na alam kung anong pronunciation ko sa Yoon, Hoyne, or something. Basta dito sa method nito. Alright? So pwede nyo explore sa project yung mga predictor-corrector methods. And there are a bunch of them. So eto na, promise ko na talaga on Wednesday when we meet for the last time, I will provide you a list of possible project topics. Ano? Pero hindi naman siya exhaustive. So kung may naisip na kayo ngayon, just push through with it. Pero kung nag-iisip pa rin kayo, just watch out for the list that I will share with you on Wednesday. Okay? And I think that's all from me today and for the course. So ang kailangan na lang tapusin, lab extra on Monday, tapos problem set number 3. On my part naman, at saka may final project pa nga pala. And on my part naman, kailangan kong tapusin grade 10, yung problem set number 2 nyo, tapos tapos na ako dun sa D2L na lab extra 5. Ano? Except for the late submissions na hindi ko pa rin nabubuksan dun sa aking email. Right? So, do you guys have any questions or concerns? All right, so kung wala na, now even the good things should come to an end. So I guess this is the end for the technical part of the course. So magmi-meet na lang tayo sa Wednesday para sa possible projects, and if you have some questions about the project, I can facilitate or I can answer them on Wednesday. All right, pero yeah. It has been a good run with you guys. I really enjoyed 174 and 175. Marami akong natutunan. So hopefully marami rin kayong natutunan. Ano? I think this is just the second time that I handled 175 lecture. Ano? So kaya medyo pasensya na nung pahuli na yung SEM, handwritten na yung mga modules, pero mas sanay kasi ako na handwritten. Yung 174 nga lang, prepared ko na yun ng 2015 pa. So hindi ko kailangan magsulat at gumawa ng lecture notes from scratch. Ano? So ito lang 175, medyo kinailangan kong on the fly gumawa ng lectures. But I hope you had fun because I did have some fun, and I really enjoyed not only doing the lectures and writing the lab exercises, but also checking your problem sets and your lab exercises. And I see the gradual improvement that you guys had. Ano? So naging masyado na kayong meticuloso ngayon sa pag-solve ng lab exercise na minsan kahit hindi ko tinatanong, nilagay nyo na para sure. And that's a nice practice, especially if you are writing a technical report or publishing a paper or whatnot. All right. So, yon. And the only thing I hope is to bump into you guys face-to-face setting. So some of you might be graduating. So congratulations. I don't know if we'll meet. Pero on-site na daw ang graduation sa CAS testimonials. I don't know if I'll be attending. But congratulations. Din naman sa mga junior pa lang, I hope to bump into you guys pag nakabalik na tayo sa math building. Hopefully sometime next year. Ano. But until then, so I hope you guys stay safe and kita-kits pa tayo sa Wednesday kung may tanong kayo about the project, all right? So bye guys.
Sir.
Thank you po, sir.